All right, in class on Wednesday, November 3rd, we started talking about power. We were talking about alpha error and beta error and the power, and we defined those. And the alpha error is something we set. It's something within our control, right? So it seems easy, just set it low, right? But we find that if we set it, if we decrease alpha, then we actually increase the beta error. They're connected. And I started to set up this example to show us why and how they're connected. And I know this is a little hard to see, so I'm just going to take you a little bit closer to it. And so we said, like, let's look at maybe the underlying distribution of the population is that the mean is equal to 50. And we just said maybe we're looking at cell stiffness, for example. In the underlying population, the mean is 50 or it's 55. We don't know which one it is, okay? But we're saying it's one or the other. Okay, so we're looking at the sampling distribution of sample means for the null hypothesis that the mu is 50 or for the alternate that the mu is 55. And we're saying that the standard deviations of the populations is both 10 for both of those situations. Okay, and I'm just going to add a subscript here so that we can keep it clear which one we're talking about. So mu here is mu naught, and mu over here is mu 1. Or how about, well, we'll keep it at mu a maybe. Okay, so when the alternate is true. Okay, and so now we said, here these are our sampling distributions of sample means, and we're looking at sample sizes of 20. And so let's say we pick out a sample of size 25 and we take the mean of that sample of 25. And if it fell in this region right over here, like way below 50 or so, we'd be like, yeah, you know what? The null hypothesis is true. But on the other hand, if we took it and the sample mean was above 55, we'd probably be thinking, yeah, the alternate is true. But this is our gray area right here. What happens when we draw a sample that has a mean in this region? How do we decide which is true? And more importantly, kind of like, well, what are our alpha errors and our beta errors? Because we really don't know what the underlying population distributions are, right? All we can do is make our best guess. So let's look at where we would make this cutoff. So if we're believing that, if we're testing H naught, which we've done a lot of times, and we're doing a one-sided test of the null hypothesis, we can set our upper bound for the confidence interval, right? We know how to do that, but let's just write it down so that we're all on the same page. So if we set alpha at 0.05, then, you know, so maybe here's 5% of the values in here or so, okay? We're going to try to find out what is our upper bound. Like it's going to be 50 something. What's that cutoff point for which we would say, okay, we're going to accept H naught here. Okay, but if it's above this point, we're going to reject H naught and favor the alternate hypothesis. Okay, so you know how to set that. This is the value of Z for which 1 minus alpha of the values are in the tail, right? So Z is equal to X bar minus mu, and it'd be mu naught here because we're talking about this distribution, okay? Sigma over radical N. And Z, I'm sorry, I'm going to erase with my fingers. This is Z, the 1 minus alpha value for that, right? And let's just solve that then for X bar. So we get our upper bound of the confidence interval. So we have X bar is equal to mu naught, let me make this right, plus Z 1 minus alpha times sigma over radical N. And if we put in our values here, mu naught is 50. Z1 minus alpha, that means Z of 0.95. We'd look at our tables and we'd find that that is 1.645. And then sigma here, I set it at 10. And then we set our sample size at 25. And we find that X bar, or the upper bound for our confidence interval, is 53.29. So this value here is 53.29, and we can write it more generally, right? Just as this, it's mu naught plus Z1 minus alpha times sigma over N, okay? So this is equal, in this case, to this is our upper bound. And just to show you it a little bit closer, there you go. So any time now that if H naught is true, we're going to make an alpha error 5% of the time, okay? That's just how it's going to be. That's what we set it at. All right, but what will happen now to our beta error? So what is our beta error now? So I just need to add in a few things here. So any time we're below 53.29, right, this is when we're in the except H naught region. Except H naught. And anytime we're below 53.29, we're in the reject H naught region. Okay, quick. There you go. All right, so now we're going to look at our beta error. So what is a beta error? So first of all, a beta error is over here, and it's like if HA is true, what's the probability that we're going to accept H naught? So if HA is really true, this curve, what's the probability that we're going to accept H naught? So we're in this region, right? So it's anything in this region right here, sorry, this is our beta error. Looks bigger than our alpha area in this case, right? That's our beta error. Okay, and so we need to quantify what is this beta error. Okay, so alpha is in green, beta error is in blue, and then of course we know that power is 1 minus beta, right? So here's 1 minus beta, so it's going to be all this area. Or we can look at our definition here, right? Given that HA is true, what's the probability that we're rejecting H naught? So it's all this area, this part in blue, or I didn't color it in blue. Let's try to color that in blue. This isn't a very good blue. But it's this part in blue, and then this part in green. All that is power, okay? So let's quantify beta first. And I'm going to just use the board right over here, to quantify beta for us. Okay, so I think we're good. So what's the beta error? The beta error, right, we're over here. It's the probability that we have a value less than 53.29 given that HA is true. So what's the probability that Z is less than or equal to 53.29 given that HA is true? Okay? And so we know how to figure this out, right? We've done this before. It's the probability, right, now that Z, which is equal to x bar minus mu, it'll be mu 2 now, because we're talking about HA is true. I should call it mu A. Make sure we're on the board. Over sigma radical n, right? And so I get the probability that Z, is less than or equal to, x bar is 53.29, mu A is 55, our sigma was 10, our sample size was 25, and we get for this, the probability that Z is less than or equal to 0. Sorry, I got that wrong. It's less than or equal to minus 0.855. Right, and that makes sense. If we look back up at here, right, we're on the negative side of the mean here, right, and we're about 1 standard deviation below. Okay, and so we find out that using our tables, we find out that that's equal to about 20%. So about 20% of the time, we're going to make a beta error. Okay, I want to just also put this in terms of like general numbers rather than specific numbers here, so we can apply it to any situation. Okay, so what's beta? So beta is equal to the probability that Z is less than or equal to this 53.29, right, is this value right there. Okay, so instead of putting in 53.29, I'm going to put in mu naught plus Z 1 minus alpha sigma radical n. Okay, okay? And then minus mu A here, okay? And actually, I think I've called it mu1 in some notes going forward, so please note that mu A we're going to call mu1 for that alternate hypothesis, okay? And then we're going to divide that by sigma over radical n. Okay, and then we're just going to do a little bit of rearrangement of this, okay, just a little bit of algebra. And so we get a general expression for beta. It's the probability that z is less than or equal to z 1 minus alpha mu naught, the quantity mu naught minus mu1 times radical n divided by the standard deviation. Okay, so that's a general expression for power. And from that we can get a general expression, that's a general expression for beta. And from that we can get a general expression for power. Let me stand up here. Okay, so I'm going to, keep this in mind. Keep this in mind, and then I'm going to show you just some of the slides that I've posted for you. If I can find them readily, I hope so. All right. Yes. No. Hang with me. How long has it been, actually? Let me see. I'm going to stop, and then I'm going to show you the slide, but keep this in mind, okay?